All right, let's talk about 6.9. Now this is the last section in this class. If you made it this far, congratulations. Good work. Keep up the good work. Okay, so let's go through it. So 6.9 is about the integral. So integration is a big topic in calculus, right? Calculus is really about two things, derivatives and integrals. And we've been discussing derivatives all semester. We haven't talked about the calculus involved with derivatives. We really only talked about kind of the algebra, the algebraic manipulations. But hopefully you're well prepped now for derivatives when you get to them in calculus. But I did want to take some time and kind of briefly introduce the idea of the integral to you, so that you're not completely blindsided by it when you get to calculus. Now, it should go without saying that in order to calculate derivatives and integrals, you need to know about limits, and so we've also talked about limits this semester a little bit. We haven't exhausted all of the details on these things, so I don't want you to walk away with the impression that this has been a calculus class. No, this has not been a calculus class. This has been an algebra class, really, where we have focused on some of the algebra that you're going to see in calculus, right? And so there's a lot of, when you get to calculus and you start talking about derivatives, there's going to be a lot of rules that you learn, shortcuts that you can take to calculate derivatives. You're not always going to be doing it the long algebraic way that we've talked about in this class. But those are topics for calculus, right? And so I'm leaving them to your calculus instructor to teach you. But anyway, same thing goes for integrals. So I just want to give you a brief kind of conceptual understanding of integrals so that you understand where you're going to see things like summation notation and that sort of thing. So let's do it. So here's the definition of an integral. The integral is the signed area between the graph of a function f and the x-axis between x equals a and x equals b is called the integral from a to b of f. We use this notation, right? So this is the integral from a to b of f of x. Okay. This little dx part of the integral is that denotes a small change in x, and we'll talk about why we have that symbol at the end of the integral maybe a little bit later on. But for more detail on that, really, you'll get more detail on that in calculus. So here's a picture, right? So let's say you have some function f, that does some weird thing or whatever, and let's say that A is here and B is there, right? So if you were interested in finding the area between this curve and the x-axis, right? So if you were interested in finding that area right there, that area is, so if this thing is f of x, right? Then this area is the integral from a to b of f of x dx, right? That's that integral. Now, why are we interested in these things? Well, lots of reasons. You'll see applications of these things in calculus. One of the applications actually is a statistics thing, because it turns out that the probability that some value is between a and b is equal to the area between the curve of the probability density function and the x-axis. So in probability and in statistics, you do a lot of this kind of integration. Well, not really, right? In an introduction to probability and statistics, you wouldn't do any integration at all. But that's where the probabilities, most of the time you're using software to figure out what these probabilities are. But what the software is doing is an integral, right? The software is doing an integral. Anyway, so that's just one application, but there are lots of other applications of integration, which you'll see in calculus. Okay. Now, when f of x is linear, computing this integral is just the same thing as finding the area of a triangle or a trapezoid. Oh, let me pause this. Okay, we're back. So yeah, we just get a trapezoid or a triangle if f of x is a linear function. So those aren't really all that interesting to look at. But what we would want to look at is, what do we do when f of x is nonlinear, right? So what do we do if f of x is nonlinear like this? So let's say that we had like this parabola, right? This parabola that's opening down like this. What we do is we approximate the area with rectangles. Okay, so let's say that we wanted to approximate this integral using rectangles. So we want to approximate the area between x equals -2 and x equals +2 of this curve, right? The area between this curve and the x-axis, between -2 and +2. So in other words, right, I want to approximate this area right here, right? So all of this area. So at first it's asking us to do this using just two rectangles. So if I just wanted to use two rectangles, then what I'm going to do, there are lots of ways that you could do this, I guess. If I draw a big rectangle that goes all the way to the top of the function, and I do that for both sides, then I'm going to be way overestimating, right? Then again, if I draw a little circle that just goes to the left side, and then a little, not circle, a little rectangle here and a little rectangle there, I'm going to be way underestimating. So what I'm going to do is I'm just going to pick an endpoint, and I'm going to stick with that endpoint. And so in this case, I'm going to use a left endpoint. So I'm going to say, so I'm going to use this as the height of my triangle, because that's the left endpoint of the rectangle. And then I'm going to use this as the endpoint, right? So since I'm sticking with left endpoints. That way I get a small rectangle and a big rectangle. Hopefully they kind of balance each other out and give me a pretty good approximation. Is this the only way to draw the rectangles to approximate the area? Of course not, right? There are other ways to draw the rectangles, and you will talk about a lot of them in calculus. But for now, I'm just going to stick with the left endpoint method of approximating. We'll see in a second that it really doesn't matter all that much what method you use. Okay, so if I want to approximate the area under the curve now, I need to find the area of these two rectangles. Well, the area of a rectangle is just width times height. What's the width of this rectangle? It's got a width of 2. They've both got width 2. What's the height of the rectangle? Well, the height of the rectangle is the function value at the left endpoint. So in this case, it would be the function value at -2 for the small triangle, and then the function value at 0 for the big rectangle, right? So, I'm going to say this integral is approximately base times height. In this case, the height is clearly 1. And here it's going to be base times height. The height is clearly 3, right? So that would be 2 plus 6, which is 8. Okay, let's look at approximating this with more rectangles. So instead of using 2 rectangles, let's say that we want to use 4 rectangles. So let's approximate this using 4 rectangles. Is this a different? No, it's the same curve. Okay, it's the same curve. Yeah, using 4 rectangles. Again, the integral between -2 and +2. So we're still trying to approximate this area, right? But this time using 4 rectangles. So obviously, if I stick with left endpoints, I'm going to have this for my first rectangle. I'm going to have this for my second one. This for my third one. And then this for my fourth one. Okay? Always using the left endpoint of the rectangle. Okay, so one thing that I might want to do is figure out what this height is. So for this one, the height is clearly 1. For this one, the height is clearly 3. But for this one, it's not very clear what the height is. So the height, maybe if I label these triangles 1, 2, 3, and 4, I need to figure out the heights of rectangles 2 and 4. So the height of the second rectangle, well, that's going to be the function value at the left endpoint, right? That's going to be f of -1, which would be f of x was, I think it was -1/2 x squared plus 3, right? Yeah. So f of -1 is going to be -1/2 times -1 squared plus 3. -1 squared is 1. 1 times -1/2 is -1/2. And 3 minus 1/2 is 2.5, right? Or 5/2. Okay. The height of the third rectangle, that's going to be, oh, the third rectangle actually, I know that height, right? So I don't need to do that one. The height of the third rectangle is just 3. The height of the fourth rectangle, that's going to be f of 1. Oh, which we should get the same thing, right? We should still get 5/2 here. Okay, very good. So then I can approximate the integral now. I can say, so the integral from -2 to 2 of -1/2 x squared plus 3 dx is approximately the sum of the areas of these 4 rectangles, right? So it's approximately, and by the way, these are all width 1 now. So it's going to be width times height. The height here is 1 plus width times height. The height here we just found out was 5/2 plus, for rectangle 3, it's width times height. The height is 3 plus, and then for rectangle 4, it's width times height. The height again is 5/2. Okay, so how much is that? So we get 5/2 plus 5/2 is 10/2, which is just 5. So we've got 5 plus 3 plus 1. So that's 5 plus 3 is 8, plus 1 is 9. So we get 9. Okay, so when we approximated with 2 rectangles, we said that the integral was approximately 8. Now that we're approximating with 4 rectangles, we're saying that the height is approximately 9. Let's say that we wanted to use 6 rectangles. Okay, so if we want to compute this or estimate this with 6 rectangles now. Well, first of all, I would need to divide this region into 6 equal parts. How am I going to do that? Well, it's going to be, the width of this line segment is 2 minus -2, right? So 2 minus -2 is 4, right? So the width of the interval is 4. 1, 2, 3, 4. Makes sense. So if I want to divide it into 6 equal parts, I'm going to do 4 divided by 6, right? So the width of each rectangle is going to be 2 minus -2 divided by 4. In other words, divided by 6. So in other words, that's 4 out of 6, which is 2/3. Why did I choose such a uneven number? So I have to do 2/3, so width of 2/3. So that's maybe there. Right, so I'm using left endpoints. I would have this, and then it would come up to about 2, maybe not exactly 2, but I have to come over another 2/3 to there. Then I have to come up another 2/3 to 0. Then another 2/3 would put me right about there. Oh, but I need to come up to 0. 2/3. Another 2/3, and then another 2/3 would bring me all the way there. Okay, so this is what the approximating rectangles are going to look like. I suppose I should find the height of each of these things. Some of them are obvious, some are not. So again, I'm going to label these triangles 1, 2, 3, 4, 5, and 6. So the height of triangle 1, that's going to be f of -2. The height of triangle 2 is going to be f of, well, what should this be? -1 and 1/3, right? So -4/3. Height of triangle 3 is going to be -2/3. It looks like is going to be, sorry, f of -2/3. Height of triangle 4. Well, that's just f of 0. Height of triangle 5 is f of 2/3. And then height of triangle 6 is going to be f of 1 1/3. So that's f of 4/3. I'm going to run out of room. This is just to get the heights. I need to still approximate the area. But anyway, I think getting the heights is the hard part. So I'm going to plug each of these values into the function value, right, f of x. All right, so I'm going to plug it into -1/2 x squared plus 3. I'm not going to write out all the nitty-gritty details. Let me just pop these things into my calculator, see what I get. So it's -1/2 times -2 squared plus 3. Okay, so that comes out to 1, which is, of course, not unexpected. Then I'm going to plug in -4/3 instead, and I get 19/9. And if I plug in -2/3, I get 25/9. If I plug in 0, I should just get 3. Yep. If I plug in 2/3, I should get 25/9 again. Let's make sure. Yep, 25/9. And if I plug in 4/3, I should get 19/9 again. So these are all the heights of the triangles. The width of the triangle we said was 2/3. In each case, these triangles have a width of 2/3. So what's the area, right? What's the integral? The integral from -2 to 2 f of x, which is -1/2 x squared plus 3, is approximately the area of the first triangle times plus the area of the second one plus the area of the third one, and so forth. Well, the area of the first triangle is width times height. Area of the second is width times height. Area of the third is width times height, and so forth. I don't know why I have such a hard time writing 25. Goodness gracious. Okay, but there's our 6 rectangles. 1, 2, 3, 4, 5, 6, right? So those are the areas of our 6 rectangles. Let's see about how much this is. So we've got 2/3 plus 2/3 times 19/9. And actually, I'm going to have that twice, right? So I'm going to kind of cut to the chase and say times 2. And then I'm going to have 2/3 times 25/9, and I have that twice, so I'm going to multiply it by 2. And then I'm going to have 2/3 times 3. Okay, so I add all of those things up. You should get 248/27, which is approximately 9.19, we'll say. 9.19. Well, so that's interesting, right? When we approximated with 2 rectangles, we got 8. When we approximated with 4 rectangles, we got 9. When we approximated with 6 rectangles, we got 9.19. So it seems like we're probably approaching some value. We're probably closing in on what the actual area is. And now what I'm going to do is I'm going to cut to the chase. So I'm going to cut to the chase. All right, and I'm going to go to this this link here that I put in your notes. So let's go to that link. And so this is Wolfram Alpha. Well, this is just one page in Wolfram Alpha, but Wolfram Alpha is a really cool math tool. If you haven't heard of it before, you should look at. You can type in like any question you want. But this particular page in Wolfram Alpha is going to graph. It's going to do what are called Riemann sums, and essentially what we're doing are Riemann sums here. We're doing left endpoints though, right? And the function that we're trying to compute the Riemann sum for is -1/2 times x squared plus 3. So I'm going to say replot Oh, but I need to do this between -2 and +2. And I'm going to say replot. There you go. Then we get this picture that we're used to seeing. Now I want to do this using not 29 rectangles, but let's just verify what we did before. If we did it with 2 rectangles, then this is the picture we get. And where does it give us the result? Oh, there it is. Estimated area it's saying is 8, which is what we got before. But it's also giving us the actual area. It's saying the actual area is 9.333. If we did this with 4 rectangles, sorry, 4 rectangles, then it gives us the estimated area of 9, which was what we got before. So we're closing in on that actual area. If we do it with 6 rectangles, hopefully we get the same thing that we got before. Yeah, about 9.19-ish. Okay, so that's if we did 6 rectangles. If we did this with 100 rectangles, we did this with 100 rectangles. Look at how close. I don't know if you can even see these numbers, but I'm going to zoom in a little. So look at how close our estimated area is to what the actual area is, right? Because if you're doing this with smaller and smaller rectangles, eventually you're going to get errors that are almost 0, right? So this is with 100. I wonder if we do 1,000. I wonder how long it'll take Wolfram Alpha to do this. Ooh, okay, there you go. So with 1,000 rectangles, it's like it practically turns black, but you can see that there's almost no error left. So now, if you think about what we're really doing here, we're letting the number of rectangles go to infinity. We're looking at the limit as n approaches infinity of this concept, right? If n is the number of rectangles, we're letting n go to infinity, right? Is what I'm trying to say. So, and that's exactly what integration is, okay? So, our estimate gets better and better the more rectangles we use. In fact, if we increase the number of rectangles indefinitely, then we get the exact value of the integral. So we're going to develop a formula for this, right? So note that when we had 2 rectangles, the width of each rectangle was 2 minus -2 over 2, which was 2. When we had 4, the width was 2 minus -2 divided by 4, which was 1. And when we had 6, we actually wrote this out earlier, but we did 2 minus -2 divided by 6, so the width of each rectangle was 2/3. If we had n rectangles, just generally speaking, then the width of each one would be 2 minus -2 divided by n, right? And so in general, this is if we're integrating between -2 and 2. But in general, if we're integrating between a and b, then the width of each rectangle would just be b minus a divided by n. I'm going to call the width of each rectangle delta x. So this little triangle is called a delta. So we're going to call this delta x, right? So delta x is the width of each rectangle. It's b minus a over n. Hopefully that makes some sense to you. What about the height of the rectangles? Well, the height of the first rectangle that we looked at was -2 plus 0 times the width of the rectangle. Okay, because that was just our starting point. It was the left end point of the leftmost rectangle. What about the height of the second rectangle? And it's the function value, right? It's the function value, as we saw, as we were working through these, right? What about the height of the second rectangle? Well, the height of the second rectangle is our starting point, right? A, -2 in this case, plus the width of the rectangle, because that's going to get you to the next rectangle, right? So if you're looking at a bunch of rectangles or whatever, what we're saying is that this first rectangle starts right at our endpoint of -2. The next one, the next height, is our starting point plus the width of the first one, right? That gets us to this next endpoint, and we want the function value there to get the height of the rectangle. For the next one, the height of the third rectangle is going to be -2 plus, not 3, this should say 2. This should say 2. So it should be twice the width right, to get us to the next endpoint, right? So it's 2 times the width plus our starting point. So in general, the height of the kth rectangle is going to be -2 plus k minus 1 times the width of the rectangles, right? So in general, if we integrate between a and b, and the height of the kth rectangle is f of t sub k, then t sub k must be a plus k minus 1 times delta x. Okay. Finally, note that the area of the kth rectangle is the height times the width. In other words, it's f of t sub k, right, the height, times the width, delta x. So what that tells us is that the total area of all n rectangles that we're using to estimate the area is going to be, well, it's the height times the width for each rectangle, right? So f of t sub k times delta x. And then we're going to add them up, right? We're going to add up all n, the area of all n rectangles. So this is the formula that we get. So with that formula in mind, now we can say what the integral is in terms of this formula, right? So let's say f of x is a continuous function, and that the interval from a to b is some subset of the domain of f. All right. This is just so that the function is well defined on the interval we're talking about. If that's the case, then the integral from a to b of f of x is the limit as n approaches infinity, right? So you let the number of rectangles that you're using to approximate the area go to infinity, right? So it's the limit as n approaches infinity of the sum of all of the rectangles that we're using to approximate the area, right? So it's going to be the sum of all the height times width, f of t sub k times delta x, where t sub k is a plus k minus 1 times delta x, right, as we saw earlier. And delta x itself is b minus a over n, as we saw on the previous page. All right, so we're just putting all these facts together to get this formula, right? So really this integral is just the limit as we let the number of rectangles go to infinity of the sum of the area of the sum of the areas of the individual rectangles, right? Height times width. Goodness gracious, wow, that's a lot of information, right? But let's do an example so that we see clearly what it is that we're talking about. So let's use the formula above to estimate the integral from -1 to 1 of 3 minus x when n equals 4 rectangles. Okay. So note that a is -1, b is +1, n is 4. So that means that delta x, right, the width of our rectangles, is going to be b minus a over n, 1 minus -1 over 4. That's 2/4, or 1/2 if you like. Okay. Okay. So that's the width. That's the width of each rectangle that we're going to be using. Right. So this is the width. What about the height of the rectangles? Well, the height of each rectangle is going to be different. The height of the first rectangle, right? Well, we're not going to find the height, I guess, but the end point, the left end point of the first rectangle, right, t sub 1, is going to be a plus k minus 1 times delta x. So that's going to be -1 plus k minus 1, right? If k is 1, then k minus 1 is 0 times delta x, which we said was 1/2, right? This is -1 plus 1/2. That's -1/2. Okay, t sub 2. The left end point of the second rectangle is going to be a plus k minus 1. If k is 2, then k minus 1 is 1 times the width of the rectangle. All right, so that's -1. Oh, shoot, I did this wrong. -1 plus 0 would be -1. This is -1 plus 1/2, which is -1/2, right? What about t3? That's going to be negative 1 plus 2 times 1/2, right? 2 here because k is 3, so k minus 1 is 2. All right. 2 times 1/2 is 1. Negative 1 plus 1 is, of course, 0. So that's the height. That's the left end point of the third rectangle. And then the left end point of the fourth rectangle is going to be negative 1 plus 3 times 1/2. 3 times 1/2 is 3/2, or in other words, 1.5. 1.5 minus 1 is just a half. So there's the height of the fourth rectangle, or the left end point of the fourth rectangle. So now what are the corresponding heights, right? So the height of the first rectangle, f of t1, that's going to be f of negative 1. That's 3 minus negative 1. So that's 3 plus 1, which is 4. Okay, the height of the second rectangle is going to be 3 minus negative 1/2. That's 3 plus 1/2, so that's 3.5. The height of the third rectangle is going to be 3 minus 0. So that's just 3. And then the height of the fourth rectangle is 3 minus 1/2. So that's 2.5. Okay, so these are the heights. They're the heights of each of the rectangles. So, so the area, right? So the integral, negative 1 to 1 of 3 minus x dx is approximately the sum from k equals 1 to 4, right? N equals 4, right? I'm using this formula right here. From k equals 1 to n. N is 4 because we're using 4 rectangles of f of tk delta x. That's the sum from k equals 1 to 4 of f of tk times delta x, we said was 1/2 times 1/2. Okay, well, f of tk, if we plug in 1, right, we get f of t sub 1, which is 4. So this is f of t1 times 1/2 plus f of t2 times 1/2 plus f of t3 times 1/2 plus f of t4 times 1/2. What's f of t1? Well, f of t1 is 4, right? So this is 4 times 1/2 plus f of t2 is 3.5, or in other words, 7/2. So 7/2 times 1/2 plus f of t3 is 3. And f of t4 is 2.5, so that's 5/2. I'm just going to plug that into my calculator now. Okay. 4 times 1/2 is 2. 7/2 times 1/2 is 7/4. 3/2 and 5/4. Okay, so you add that all up, you should get 13/2. 6.5, right? However you want to say it, 6.5. So there you go. There's our estimate, right? So very interesting. Okay. Now, in order to get an idea for the value of the limit as n approaches infinity of this thing, we could estimate the area with 2 rectangles, and then with 4 rectangles, and then with 8 rectangles, and then with 16 rectangles, and then we can make a table of values and see what number we're approaching. Obviously, this would be incredibly time-consuming, and there's no guarantee that we would end up with a precise answer, right? Like, what if the area you're looking for is like, 2 times the square root of 17 or something, right? Like, you're not going to get a precise answer by using a table of values, right, to see what value you're approaching. So the alternative is to think a little bit more abstractly and flex our algebra muscles a little bit, okay? So we're going to do this with a very simple function, just x, right? So so we're going to use the characterization of the integral on page 4 on the previous, or on page 3, right, on the previous page, to find the exact value of this integral, the integral from 0 to 1 of x dx. This is something that we could do easily by hand with a little bit of geometry, but I just want to show you that the formula works, right? So let's let n be the number of rectangles used to approximate this integral. Then delta x in this case is going to be b minus a, right? Note that b is 1, a is 0, and n is, well, n, right? We're just letting it be n abstractly. But delta x would be b minus a over n. That's 1 minus 0 over n, or in other words, just 1 over n. Okay, so delta x is 1 over n. Also, t1 would be 0. t2 would be 0 plus 1 over n. So that's just 1 over n. t3 would be 0 plus 2 times 1 over n, or in other words, 2 over n. And in general, tk, well, maybe it would be helpful to do a few more examples, right? So t1 is 0, or in other words, 0 over n, right? t2 is 1 over n. t3 is 2 over n. It seems like we're going 0, 1, 2 in the numerators, and the denominator is always n, n, n. So it seems like the numerator is going to be 1 less than our subscript on the t, right? So tk, it seems like it's going to be k minus 1 over n. Thus, the area of the kth rectangle is f of t sub k times delta x. Well, f of t sub k, f of x in this case is just x. So f of t sub k is just t sub k. And t sub k we just figured out is k minus 1 over n. So f of t sub k, it would be k minus 1 over n times delta x. What's delta x? Delta x we said was 1 over n. So in other words, that would be k minus 1 over n squared. So the sum of the rectangles would be the sum from k equals 1 to n of f of t sub k times delta x. That would be the sum from k equals 1 to n of k minus 1 over n squared. All right, that's what we just figured out. Okay, now this sum can be, since n squared does not change with k, we could pull out the n squared, right? In other words, I'm kind of thinking of it like this. 1 over n squared times k minus 1. But the 1 over n squared does not change with k, so we can pull it out of that sum. We can factor it out of the entire sum. So it's going to be 1 over n squared times the sum from k equals 1 to n of k minus 1. Well, what is this sum, right? If we plug in 1, we get 0. If we plug in 2, we get 1. If we plug in 3, we get 2, and so forth. So it's going to be 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way until we get to n minus 1. So the sum of 1 plus 2 plus 3 all the way to n minus 1. Notice that this is an arithmetic sum, and we learned in the previous section that it's equal to n minus 1 times n over 2, right? We talked about that formula on in 6.8. So this whole part of the sum, or this whole sum, can be replaced with this expression, n times n minus 1 over 2. So, putting it all together, the sum of f of t sub k times delta x is really the same thing as 1 over n squared times the sum from k equals 1 to n of k minus 1. That sum is equal to n minus 1 times n over 2, right? This sum gets replaced with this formula, right? So you get 1 over n squared times n times n minus 1 times n over 2. Now we can cancel off an n. We get n minus 1 times 1 over n times 2 is 2n. Now, that's this sum right here. The question is, what's the limit as n approaches infinity of this sum? Well, the limit as n approaches infinity of this sum, we decided that this sum was equal to n minus 1 over 2n. What's the limit as n approaches infinity of this sum? In other words, what's the end behavior of this rational function? Well, we talked a lot about the fact that when your degrees are the same, the end behavior is just the ratio of the leading coefficients, in this case, 1/2. Okay? So, what does that tell us? That tells us that the integral from 0 to 1 of x dx, right, by definition, that's the same thing as the limit as n approaches infinity of the sum k equals 1 to n of f of t sub k times delta x. That we decided was 1/2, right? So the integral from 0 to 1 of x dx is just equal to 1/2. We can verify that by doing just a little bit of geometry, right? If we look at f of x equals x, it's just this straight line right here. If we're looking at the area between 0 and 1, right? So if we're looking for this area right here, well, that's just the area of a triangle. The area of the triangle is 1/2 base, right? The base here is 1 times height. The height of the triangle is also 1. Well, that's just 1/2, right? Sure enough. So a little bit of geometry verifies it. What's nice about this formula that we have, though, right? This formula for the integral. What's nice about it is that it allows us to find the area under a curve when you have something that's nonlinear, right? Obviously, if you have a linear function, you can always just find the area of a triangle, but if your function is nonlinear, you can still do this process. It's a little bit more complicated, right? So I'm not going to take you through any more examples of it, of using this formula in this class. You'll do some more of this in calculus, but it is nice to know that it does in fact work, at least in this case. So anyway, one of the sort of troubles of introducing this concept here is that you might go into calculus thinking that calculus is going to be impossibly difficult. It's going to require you to do all of this really nasty algebra all the time. And let me just reassure you that that's not actually the case. In calculus, as I said at the beginning of this lecture, you're going to learn a lot of shortcuts and tricks to make this whole process a lot easier. The biggest shortcut of all is called the fundamental theorem of calculus. And it's one of the coolest theorems in all of mathematics. So before we talk about it, though, a little bit of background, okay? And this is all just loosely speaking, but a little bit of background. So the derivative of a function is the instantaneous rate of change of the function. We talked about that way in chapter 1, right? When we talked about derivatives. But it's the instantaneous rate of change of the function at a particular value. The integral of a function is the area between the graph of the function and the x-axis. Okay? At first glance, it doesn't seem like those two things are related at all, right? But the fundamental theorem of algebra tells us that they are related, that they are in fact inverse operations of one another. Okay? So here's what the fundamental theorem of algebra or of calculus says, loosely speaking. So the fundamental theorem of calculus tells us that the derivative of the integral of a function is just the original function. So the derivative of the integral is just the original function. And on the other hand, the integral of the derivative of a function is just the original function back, right? In particular, if you're taking the integral from a to b of f prime of x, that's just f, not f prime, that's f of b minus f of a. Okay? So that right there is the biggest shortcut that allows us to find an integral. If we can figure out what the antiderivative of a particular function is, then we can find the integral of the function by just plugging in, by finding the antiderivative and then plugging in the endpoints. So we can avoid doing all of that work that we did on the previous page if we can figure out what an antiderivative is. Consequently, in calculus, you're going to spend a lot of time talking about antiderivatives, right? But the reason for that is because integrals are the same things as antiderivatives, loosely speaking, right? That's what the fundamental theorem of calculus is telling us. So in other words, the integral and the derivative undo each other. If you start with a function and you take its derivative, and then you integrate the derivative, you're going to end up back with the original function, loosely speaking. Right? There are some details, right, that we're kind of glossing over, but and your calculus instructor will go over those details with you. But the moral of the story is that this is just a really nice shortcut, and it's a really interesting fact, right? That you have these two things that are completely unrelated, that seem completely unrelated, right? The instantaneous rate of change of a function and the area between the graph of the function and the x-axis. They seem completely unrelated, but they turn out to be inverse operations of one another. That's just really cool. If you're not blown away by that fact, it's because you haven't thought about it enough. Okay, but it's a really cool fact. And it's helpful for calculating integrals. So let me show you how this is helpful. So let's say that you have a derivative, f prime of x equals 3x squared plus 6x. Now, this is the derivative of several different functions. One of the function that it's a derivative of is this function, f of x equals x cubed plus 3x squared minus 2. You're welcome to verify this fact if you like. So if you could take the derivative of this function, I promise that you're going to get 3x squared plus 6x. So let's use that fact to calculate the integral of 3x squared plus 6x between negative 2 and 3. Okay, what the fundamental theorem of calculus tells us. So basically what we've got here is the integral of a derivative. Well, the integral of the derivative is just going to be the original function that we're starting with, right? Evaluated at 3 and at negative 2. So let's do it, right? So the integral from negative 2 to 3 of 3x squared plus 6x dx is going to be f, not f prime, right? Not 3x squared plus 6x, but f, the original function, f of 3 minus f of negative 2, right? That's going to be, that's going to be f of x. So that's going to be 3 cubed plus 3 times 3 squared minus 2, right? There's f of 3 minus f of negative 2. So that's going to be negative 2 cubed plus 3 times negative 2 squared minus 2. Right? That's that integral. So instead of having to do all this summation notation and then taking limits and stuff, we can just apply the fundamental theorem of algebra. Okay? So this is 27 plus 3 squared is 9. 9 times 3 is 27 again. Minus 2. Negative 2 cubed is negative 8. Negative 2 squared is positive 4. Plus, or times 3 is 12. Minus 2. So we've got 27 plus 27 is 54. 54 minus 2 is 52. Negative 8 plus 12 is 4. 4 minus 2 is 2. So we've got 52 minus 2. That's just 50. Okay, so that's that integral. It's 50. So the area between the graph of this parabola and the x-axis between negative 2 and 3 is 50. Okay. That's the claim that we're making. So it's, and it turns out to be true. It's really pretty interesting. But so that's that. That's all I'm going to say about that. One of the things that you might be asking yourself is, okay, this is all well and good, but if you weren't given the original function, if you were just asked to evaluate this integral, how in the world would you figure out that the original function here was x cubed plus 3x squared minus 2? The answer to that question is you take calculus. You take calculus and you figure out how to get from here to there, right? That's the real trick. That's the real process, and that's a topic for you to discuss in calculus. But anyway, I just think it's really interesting. The fundamental theorem of calculus is really interesting, right? Derivatives and integrals undo one another, right? So it's a really interesting fact. So that's all I have to say, not just for this section, but for this entire class. We've reached the end. Congratulations, and good luck with all of your future endeavors.